I'd like to go through some theory with you. All right, so in our last prac we looked at the IV characteristics of a circuit. We had an ohmic and a non-ohmic conductor, one of which would follow Ohm's law, and of course an ohmic conductor would be a linear graph, IV graph. Some of you got pretty close to a linear graph. Others, for the incandescent light bulb, results would vary, but it certainly was not linear. It wasn't supposed to be. So let's just go through a few things. And first of all, resistance is a measure of how hard it is for current to flow through a particular material. Does that mean that it won't flow through the material? No, it just means that it's obviously going to it could slow the current down as such. If it was enough resistance, yeah. For example, an insulator is a very good example. Something with a high resistance. Absolutely. Now it's measured in ohms, and of course ohms comes from George Ohm in the, I think it was the 1700s. I'm not sure if it says it there, but George Ohm, I believe he was German. And he had a lot to do with proving that there was a relationship between voltage, current and resistance. He also had shown that, for example, the higher, or the relationship between resistance and the heat in a wire, okay? The heat in the wire, as it turns out, the hotter something is, the more it actually also, the temperature of the conductor also had a big effect on the resistance. Now, I guess if you think about it, for electrons to move from one place to another, they need to first be separated from their atoms and then given energy to move. Now, of course, conductors tend to have a high rate of they're able to obviously accept electrons, donate electrons, and so on. So, and of course, in conductors, the amount of energy required to do this is negligible. So, for example, if I had copper, now let's think about copper. And does anyone know where copper would lie on the periodic table? Is there a periodic table in here? Well, let's start thinking about electrons. Let's think about electrons. How many electrons in the first shell? There was 2 electrons in the first shell. An example of 1 electron in the first shell and a proton was hydrogen, wasn't it? Hydrogen, helium, lithium, beryllium, boron. Is it carbon? Okay. All right. Carbon is 6. Good. What about copper? Is copper plus? Well, copper is, well, actually it's a neutral element, but of course it can gain or it can lose 2 electrons quite easily, I think. So if a copper lost 2 electrons, it would become what we call an ion, wouldn't it? A positive ion. So let's just say in the second shell, let's just say if I had so if I filled the first shell and then I had 1, 2, 3, 4, 5, 6, 7, or let's just say we had 8, okay, and then the next shell we had just 1 electron. What's likely to happen with that 1 electron if we give it some energy? Yeah.
It would be moved from the atom in order to gain a full valence.
Absolutely, full valence shell, absolutely. So if we omit that electron's going to be quite happy, okay, because it's there by itself. Oh, I'm by myself in the third shell. Okay, so that's the whole idea. Now, the actual electron movement is quite random, but of course we've got millions and millions of billions of electrons, and of course even when current isn't flowing, those electrons are still tending to move around due to just thermal effects. And that's why I said that there are some thermal effects. The thermal effects does have a lot to do with the electron movement as well. And at a random with a great speed. Now we might have a look at a small thing to discuss electron speed through a conductor. We might not, depending on time. Variables that affect the resistance. Now I guess this is a bit of an extension. I will say to you that at this stage you are not required to memorise this formula, but resistance has a lot to do with, first of all, the length of the wire. Okay? It also has to do with the cross-sectional area of the wire. Let's have a look at this. You could say that resistance is inversely proportional to, this proportional sign you'll see a lot in physics, is inversely proportional to the cross-sectional area. In other words, if I have a big area would mean a big resistance, wouldn't it? Sorry, a very small resistance. If I had a smaller area, it would have a larger resistance. Okay, small number here means big number there. Okay, resistivity is what we call this, I think it's rho. This is the resistivity, and that has to do with the properties of the material. So, for example, copper might have a low resistivity, being a conductor. Glass might have a high resistivity because it is it's certainly not a conductor. It's not a complete insulator either. As we said, though, once again, temperature will affect resistance. And look, there's a complex formula here I'm not going to go through. We don't need to know. But it's important to know that it does affect the resistance. Now, as you can see, I had a bit of a discussion yesterday that, you know, the cooling fan on a computer motherboard circulates around. And, of course, we've got a lot of components which are very close to each other. We've got, at times, you know, a fairly, not a very fast-moving electrons and current, which is all very close to each other. So, of course, a cooling fan is required. So it does, of course, more resistance does affect, of course, the temperature of the conductor as well. Now, we had a look at incandescent light globes, and what did I mention? I mentioned that now what are we looking for? We're starting to use things more efficient ways to generate light, such as LEDs and fluorescent light tubes. Okay? And, of course, the incandescent light bulb, the reason why we tend to have... Does anyone know the element that they used to have in the old light bulbs? It starts with T. Tungsten. Why would they use tungsten?
High melting point.
High melting point. Very good. Now, of course, you know, are we going to ask you why they use tungsten? No, but it's a nice to know. Okay. The high melting point. Why? Because when current flows through it, what happens? It glows. Okay, and then we obviously don't want the tungsten filament to burn out, do we? Okay, so that's why they tended to use those. Now, so for example, though, if the temperature and resistance, increasing the temperature of a piece of copper wire means that the copper ions will vibrate back and forth more quickly. In other words, we've provided there's more energy within those copper ions, and that makes it more likely that an electron will collide with the ion as it moves past it. Therefore, increasing the temperature of the wire also increases the resistance of the wire. So we could almost say that the temperature we could say that the resistance, more or less, without having to memorise some formula which we don't need to know, the resistance is proportional to the temperature in the wire as well. So there's going to be that effect. But of course, we really are looking at the relationship between voltage, currents and resistance, and that's Ohm's law. Now, you might see it as a number of ways. You could see it as the change in voltage. Well, that's not really a change in voltage. That's what we call a potential difference. A potential difference. Which we're certainly going to get to a little bit later as well. And of course, you guys in Year 9 would have seen this, so you didn't have to rearrange formulas. I don't want you to. We have to be able to rearrange formulas ourselves, okay? But voltage equals the current times the resistance. Resistance is equal to the voltage times the current. If your maths was really bad, then of course you could say, okay, if I wanted to find the resistance, I could cover this up and I could say that the resistance is equal to the voltage over the current. Now, I don't really expect Year 11s to be that elementary, so rearranging equations is something that you guys will need to get good at if you aren't already so. Now, just quickly, now we'll go through some examples, that's fine, but we then, in the prac that we did, we had a look at ohmic and non-ohmic conductors. Ohmic conductors are usually called resistors. So, of course, our ceramic resistor that we had was an ohmic conductor. We should have had an IV graph if we gathered our results correctly and measured, for example, the supply voltage, what actually was coming out of the DC power supply. And we should have got something which looks pretty linear. Now, I discussed yesterday that if I was to take the rise over the run, okay, if I was to take the rise over the run, really that's the same as, I guess, the change. If I looked at two intervals, change in current over the change in voltage, if you like. And as it turns out, Mr. Ohm and other physicists had then decided, well, that is equal to 1 over the resistance. Okay. Now, if I do the bit of the old flipperoo, okay, if I flip that over here, or if you like, if I could cross multiply, but resistance is equal to the voltage over the current. Voltage in volts, of course, and current has to be in amps. A lot of the time we might deal in milliamps, microamps, and etc. So, now we're going to have a look at some examples of using Ohm's law to calculate current, potential, current, resistance, and so on. But you might recognise, if I go a couple of pages over, that this is sort of what we would have expected, this graph here for our light bulb. Okay? Maybe you didn't get that. That is what we call a non-ohmic conductor because it's not a linear graph, it's not a straight line. We can still find, however, the resistance at a particular point. For example, if I get a nice easy one here, let's go ahead over here. If I wanted to find the resistance, now the resistance is going to vary, okay, at different voltages and currents, okay? If I wanted to find the resistance of the light bulb, when V is equal to 5 and I is equal to 3 amps, how do we do that? Well, let's have a look at 5 volts. 5 volts up here. And that roughly marries up to, yep, 3 amps. And you can see there that what is happening as I supply more current to the circuit, do you think? What happens if I'm supplying more current? What's going to happen to the filament in the light globe? It's going to heat up. Heat up means more resistance, yeah? Now, that's why it's a non-ohmic conductor, because of the fact that it changes. the resistance changes. It's not constant. So what we can say then is that the resistance at 5 volts is equal to V over I, which is equal to 5 over 3, which is, if you like, 1 2/3 amps, 2/3 ohms, which is a very small amount, or we could say it's 1.67 ohms if we're rounding off to 2 decimal places. So if you have a non-ohmic conductor, the only way you're going to be able to find the resistance at any point in time, whether with different voltage and current, is when we use the graph. You'll be given a graph. It's a standard exam question. Find the current, find the resistance of this ohmic conductor at this point. Of course, if I had, and look, this is also summarised here. They said that the resistance at 6 amps, resistance of the ohmic, no, they're talking about an ohmic conductor. If I go back though, you can see there for an ohmic conductor, the slope, the inverse of the slope, would give you, if they asked you to find the resistance, I know that I over V is equal to the rise over the run, if you like. Rise over the run. So I could get that from that graph, but just be careful. So if I said, if I get a nice point, say here, that looks to me as though that is 3 volts, that is 1.5 amps. So it rises 1.5. The run is 3. Now that is the same as 1 over 2, isn't it? Which is 1 over 2. So therefore, what would be the resistance? Well, that is I over V. What is resistance though? Resistance is V over I, isn't it? Which is 2 over 1, which is 2 ohms. Now you notice that the rise over the run for a straight line is going to be the same, isn't it? Okay, so of course if you've got an ohmic conductor, it's much easier. Now if we have a look at this example here, what's missing? This is using Ohm's law to calculate resistance and stuff. The table below shows the measurements for the potential difference of an ohmic conductor. Ohmic conductor, Ohm's law applies. Ohm's law applies actually for the non-ohmic, but of course it's not going to be linear. So if we go from 0.2 amps, and I'm going from 3 volts to 9 volts, given that V is proportional to I or vice versa, we can say, what's this current going to be? 9 divided by 3 is 3, so we know that it's going to be 3 times larger than the voltage at 3. So that's going to be 0.6 amps. What about this one here? I've got 0.8 compared to 0.2. That's 4 times larger, isn't it? So V2 is going to be 4 times larger than the voltage here, which is going to be equal to 12 volts. Does that make sense? I hope so. And so once again, I could be given, a similar sort of question. So that's finding it on an ohmic. Now, just quickly, you guys, I'm not going to tell you the rude one that I remembered when I was a boy, but we have a resistor colour code. Resistors are very small. You guys can come up with a mnemonic to remember this, but I'm not going to tell you my mnemonic. You can make one up yourself. I'll say it off camera. Okay? I can't think of the clean one. But what it means is that if the very first symbol of the very first colour of a resistor is brown, it means that that's a 1. The second one is a green, means that that's a 5. So that's 1, 5, and the third one is the multiplier. How many zeros do we have? So orange means 3 zeros, so that's the equivalent of 15,000 ohms. And the last one is the gold thing is actually a tolerance level. So it's going to be between 15,000 ohms plus or minus 5%. So I will say, there we go. So that there is a 15 kilo ohm resistor. So if we ever had to play around with them and measure resistors, we might get some resistors out, measure with a multimeter the resistance and see how close it is. A lot of the time it's going to be within that tolerance level pretty much every time.
Rabbits often yield great big vocal groans when gingerly slapped.
There you go. So what was that one, Daniel? That's pretty nice. What's that?
Oh, we're recording. Big brown rabbits often yield great big vocal groans when gingerly slapped.
So, well, you know what? You don't probably need so, just one sec. What we're really concerned about is not the gold and the silver. We're really concerned with the colour. The colour. So I would stop at W for white. Okay? So now we might have a look at that as well. Now, just quickly, the last thing is, you're going to now, in section 3.4, you're going to have a lot of questions like, a current is drawn, find the resistance. It's just using your Ohm's law, which is your formula V equals IR. So, for example, here's a go. Using Ohm's law to find the potential difference. First of all, when doing these questions, highlight what you've got, please. Make sure that you write out what you've got. A torch has a resistance of 5.7 ohms. It draws a current of 700 milliamps. Okay? So what you do is you would say that resistance is equal to 5.7 ohms. You then say, however, that the current, don't go writing 700 milliamps because we know that the current has to be in amps. 700 by 10 to the minus 3 amps. Calculate the potential difference. So we know that R, Ohm's law, is equal to V on I. We can rearrange that equation to be V is equal to I times R, which is 5.7 in ohms times 700 by 10 to the minus 3. Work that out in your calculator and away you go. I'll try to work that out in my head. 700 times 5 is what? 3,500. 0.7 times 700 though is 490. 490 plus 3,500 is 3,990 times, though, 10 to the power of minus 3. That hasn't gone anywhere. What would I do to the decimal point? I've got it here at the moment. What would I do? Chuck it back 1, 2, 3. Okay, beautiful. 1, 2, 3. So I've got 3.99 volts. Now, of course, that's not that bad, is it? Is that what your answer is? I hope so. I think I'm going to tell you it is. All right. Are there any questions? Are there any questions? All right. I'm going to, if you can just manipulate Ohm's law, if you can, of course, if you've paid attention to what I've said, ohmic and non-ohmic conductors, you should have no problems in doing the exercises from 3.4. I'm going to stop this video now, and of course it did go for much longer than I hoped, a lot longer.